Greetings and welcome, internet friends. Mr. Waddy hanging out in my Lego room. Got all my Legos on display on shelves. It's pretty wonderful. It's an inspiring environment to be doing math in. It's just bringing joy. Although, to be honest, I miss being in the presence of my students and just having good times hanging out together, doing math with my algebra buddies and G-amigos. Taking a look at last night's quest. This is from Alg1.09.01, talking about properties of radicals and cubed roots and simplifying things like that. Here we go. It says question 7, determine whether the expression is in simplest form. Explain why. And so is 48 simplified? I'm gonna say no. Oh man, crazy tablet. No, because 16 goes into it. Goes into 48. And actually, even if I didn't notice 16, wait a minute, 16 does go, okay. Yeah, 16 goes in. Even if I didn't notice that, 4 would have gone into it, and I could have reduced it over a couple different attempts. Just like with fractions, you could partially simplify and then simplify further. Same thing with this. If I didn't notice, actually, guys, this is just too good. Let's say I did the 4 thing. So if I broke this up into the square root of 4 times the square root of 12, I would have been like, aha, square root of 4 is 2. And then I'd be like, maybe I would have thought this was the answer, but no. Because 12 can be further simplified. Yeah, 4 goes into 12 3 times. And so I would have had 2 times 2 times 3. 2 times 2 is, right, a total of 4. And so eventually I'd still get the same exact thing as if I broke it up into square root of 16 times the square root of 3. I would have gotten 4 rad 3 much quicker this way if I chose the largest perfect square. But I'm getting ahead of myself. They didn't even ask me to simplify it. They just wanted me to explain why. How about this one? I'm going to say no. Radical... bam in denominator, right? We don't allow that. We don't allow that. And so the trick here would have been multiplying by rad 2 over rad 2, giving us something that would simplify. And so when dealing with square roots, you're gonna need to be familiar with your perfect squares. So whether you've generated a list for yourself somewhere, looked it up online, something, you're gonna want to have those on hand mentally. And so here, if I want to simplify the expression, I'm going to try to find the largest perfect square that goes into this. And so in the case of 20, I could break it up into the square root of 4 times the square root of 5. And I like the square root of 4 because it will reduce with this square root. Square root of 4 is 2. Rad 5 is irreducible. 48. Didn't I just have 48 a second ago? I did. Ooh. So square root of 48, I could break up into 16 times 3. And n to the 5th, we talked about this. I could say n squared times n. But even simpler is write it as n to the 4th times n. Because I just need to pick the largest exponent that is divisible by the index. The index is the number, the little number of the root. And so if it's a square root, the index is an invisible 2. If it's a cubed root, the index is 3. If it's a 4th root, the index is 4. And so let's simplify. Square root of 16 is 4. Square root of n to the 4th is n squared, because n squared times n squared is n to the 4th. And then the parts that can't be simplified, we'll combine them back into a larger radical. And so square root of 3n. There you go. There you go. Let's keep cruising. So here, we also discovered you can distribute a radical not only over multiplication, but over division as well. And so, tell you what, I can break this up all over. And now, oh man, now I'm working horizontally instead of vertically. Whatever, it's fine. Square root of hundo is 10. Square root of 4 is 2. Square root of x squared. At this point, we're calling x, and we'll explore some interesting possibilities about that in the future. Now, when dealing with perfect cubes, cubed roots, sorry, I need to be familiar with the list of perfect cubes. And so cubed root of -64. Now, that might be a little bit unusual to you because you can't take the square root of a negative and get a real number answer. Foreshadowing. But you can take cubed roots or fifth roots or seventh roots of negative numbers, and it'll work just fine. And so 64 itself is a perfect cube. The cubed root of, well, tell you what, I'll write it down. Square root of negative, or cubed root of -64 times the cubed root of x cubed times x to the what? Squared, right? Because 3 plus 2 is 5. And why did I choose x cubed here rather than x to the 4th? Because I wanted something, an exponent, that was going to be divisible by the index. And 3 is divisible by 3, but 4 is not. Cubed root of -64, well, cubed root of 64 is 4. Cubed root of the negative will still be negative. Cubed root of x cubed is x, and I'll be left with the cubed root of x squared inside the radical. Over here, this minus sign's not even in the radical, so it's just going to be hanging out. So I'll have the cubed root of 81. Is 81 a perfect cube? No, but 27 goes into 81. Let's see, I'm going to write this minus sign before I forget it. 27 times what is 81? Well, that's 3. How about y squared? Can I break that into a perfect cube? No, I cannot. Cubed root of 1,000, that is a perfect cube. And the cubed root of x cubed, I don't have to break that up because it already is a perfect cube. So let's see what happens when I simplify. So this will be negative. Cubed root of 27 is 3 because 3 times 3 times 3 is 27. Cubed root of 3 does not simplify, right? That's a 3 to the first power. No go. And so, hey, tell you what, let's combine it with this one, the y squared, which also I couldn't break down into something divisible by 3. Cubed root of 1,000 is 10, and cubed root of x cubed is x. And I notice if I could distribute the 3 and the 10, I should, and I can never distribute a radical with something that isn't in the same radical. All right, ooh, here we go, example 4. These were the tricky ones. Well, actually, square root of 48. Tell you what, there's a few different ways you could have done this. Let's simplify square root of 48 first. I think 16 goes into it 3 times. And so I would have had rad 5 times 4 rad 3. Now the problem is, I've got a radical in my denominator. And so I'm going to have to multiply by something equivalent to 1, so it doesn't change the value of the expression, but we'll somehow get rid of this radical. And so we had some good tricks we learned, and in this case, I'm going to multiply by the square root of 3 over the square root of 3, because rad 3 times rad 3 is the same as the square root of 9, and the square root of 9 will simplify. Now notice, I don't have to multiply by 4s here. That's unnecessary. I was cool with the 4 being in the denominator. I'm fine with that. And so if I did this, I would then make my fraction less simplified, and then I'd end up having to reduce by 4s again later. If you made that mistake, that's fine. Like, you'll still get there eventually, but yeah, save us some steps. Square root of 5 times square root of 3 is rad 15 over 4 times rad 3 times rad 3. Whether you think about that as the square root of 9 or the square root of 3 squared, and the square and the square root cancel out. Either way, you get 3 left over. And so I'll have square root of 15 over 12, final answer. And I cannot simplify 15 and 12. Yes, I agree 3 goes into 15 and 12, but one of those is in a radical, the other is not. All right, tricky. Here we go. I'm going to write this 25 as being 5 squared. And so since this was a cubed root, I'm going to have to multiply by a cubed root to get any work done. But if I multiplied by the cubed root of 25, 25 times 25 is, well, whatever it is, it's not a perfect cube. All right? Not going to be a perfect cube. And so I want to multiply by something that will give me a perfect cube. So I could have, if I'm clever, right, I could have even done it up here. I could have multiplied by the cubed root of 5. And that's because 25 times 5 will give me 125, which is a perfect cube. Another way you can think about it is, oh, let me just write this in its kind of prime factorization, something like that. Try to break that up. Oh, 5 squared is how I could represent that. And then I need to multiply by some version of 5 that is going to give me a perfect cube. And so 5 squared times 5 to the first, 2 plus 1 is 3, and that's going to work out. Let me get rid of this up here because I don't want to make it look like I did this twice. And so I'm going to multiply by the cubed root of 5 over the cubed root of 5. Got to multiply top and bottom because that is equivalent to 1, and it's going to be able to cancel out. All right. So 4 cubed roots of 5 over the cubed root of 5 cubed, or the cubed root of 125 if you wrote it that way. That's 4 cubed roots of 5 over, that's just 5. And this 5 doesn't cancel with the 4, and so I'm good. I'm good. All right. Hope you all having a good time. Take care. Calculator.